Yeah. So uh, yeah, let me start then. Uh,
Yes.
yeah, so at first, yeah, once again, I would like to thank all of you for giving me the opportunity to present my work. My work is mostly concentrated on color generation with all dielectric asymmetric metasurface. And in this presentation, firstly, I want to show you the outlines, which means that what I'm going to cover in this presentation. So initially, I will give you a brief idea about structured colors, how it can be generated, what is the motivation that lead me to conduct research in this area. And then I will show you some recent research in this field. Afterwards, I'll show my design and results what I could produce out of it. Then obviously I will briefly show you the methodology that I have followed to do the research, and at the end there will be conclusion. So now let me move on to the next slide, where in the introduction section, so where I have pointed out few questions which I will be answering you one by one. So the first thing is that at first, just to give you a brief idea that what does color mean. Color is nothing but it's a medium, or it can be said as a carrier through which we actually convey our visual information and we perceive the world, and it is dispensable to our daily life. That's because we should know that how these sort of colors can be generated, what mechanisms are involved in it. So basically, in principle, there are three mechanisms by which colors can be generated. Firstly, by reflecting or transmitting a particular or desired color from a substance by absorbing the others. Secondly, it can be generated from different based on different phenomena like scattering, diffraction, or dispersion. And lastly, it can also be emitted using luminescent, photoluminescent material. So whichever way the color is being generated, it interacts in our eyes, and a human eye senses this color with the help of photoreceptors, or it can be also termed as cone cells. And there are three cone cells in our eyes which actually respond to different wavelengths of color stimuli. And there are actually three different ranges of these color stimuli, which basically covers between ranges between 564 to 580 nanometer, 534 to 545 nanometer, and 420 to 440 nanometer. However, in simple words, it can be said that human color perception can be termed as an additive combination of the stimulation of all these three types of cone cells, and thereby any of the color stimuli can be reproduced by appropriately mixing three of the primary colors. For example, in standard RGB, if you just appropriately mix the red, green, blue color, you can reform a particular or your desired color or reproduce actually. So this is how colors can be generated. Now let me move on to the motivation or the underlying motivation due to which I have designed a structure, colored structure. So actually, there are various structures. They are already available that can produce spectral or visible colors. However, the motivation behind my work is to achieve pure visible colors by utilizing high Q resonance. So the idea was to design a simple structure that could support high Q resonance. And how I have achieved it? By tuning or just by scaling some geometrical parameters to cover the full visible spectrum so that I can get a wide color gamut. So this was the main motivation behind my research. And now let me move on to the next question, which is about approach. What approaches are previously followed was based on flowers, pigments, and dyes. Those are previously used to generate colors. But the problem with this method was with that approach was that it suffered from low resolution. It has got poor resolution. Also, it was not chemically stable at high temperature. And some pigments are also toxic materials, which is not environmental friendly. So because of these reasons, pigments, dye-based colors, the applicability was being limited due to these demerits. Therefore, just artificial structure color generating nanostructures have appeared as a suitable or promising alternative to dyes and pigments, just to overcome all these limitations. So, however, in this work, I just tried to design a structure with dielectric material, which possesses suitably high refractive index and especially low loss in the visible region, and from which I can expect that it can give me, or I will be able to produce bright and pure colors, and also get large color gamut, which I'm trying to, what I'm trying to mean that a large color coverage area, which targets to achieve the full color spectrum. So this is all about the approach, and obviously there are some limitations to achieve such pure distinct colors. So up until now, there is no structures actually such structures being proposed that can completely satisfy all the requirements of commercial applications of these structure colors, which basically needs to fulfill few characteristics, like colors needs to have high brightness, it needs to be distinct with diffraction limit, high resolution, it needs to cover a large color gamut, and also manufacturability was one of the issues, or one of the characteristics that needs to be filled in. However, research is still going on, or it's still being carried out on such nanostructures to fulfill industrial requirements and make it more feasible, or reasonably feasible, or make it available at reasonably low cost and at a broad scale. So this is all about the limitations. Now let me move on some recent research that has been conducted in this area. So as I have mentioned, that various researches have already been performed on structure color. So, but I will be highlighting on three researches that has been carried out most recently in between 2017 to 2020. So here the first work, as you can see, the first work is related to all-dielectric printing structure, which I'm trying to mean that they have proposed all-dielectric color printing by means of a dual color pixel, which they have achieved by changing the polarization of light by varying the dimensions of these nanoblocks. So, and by doing so, they try to achieve relatively pure colors. And the material, the structure is fabricated basically based on silicon monocrystalline, which is deposited on quartz substrate. And however, there is some limitations of this work. What I could realize that it suffers from a poor resolution, and it could produce colors with relatively low intensity. So then let me talk about a bit about the second work that has been done related to the structure color. So the main motivation of this work is to suppress higher order Mi resonance outside the main reflection peak. And how they achieved it by proposing a structure with silicon nitride and quartz, where they have tried to pick these two materials in a way that they could reduce the refractive index contrast. By doing so, they tried to reduce the appearance of higher order modes outside this this reflection peak. So by doing that, they could produce relatively pure and efficient colors, which are applicable, which they proposed are applicable in eyewear displays. However, this work has also got some limitation due to since the colors those are produced based on this structure has got a low Q factor, which ultimately leads to small color gamut. So which means that they couldn't cover the full color spectrum, visible color spectrum. So this was one of their limitations, as I could understand. Then yeah, this is all about the second work, and then let me move on to another work which is published in Nature Communication in 2020. So in this work, what they have done, they tried to combine two things. One, they tried to introduce a refractive index index matching layer just to reduce reflection from the substrate. And another thing, what they have done, they have introduced a background material, which is here PMMA, which stands for polymethyl methacrylate, or they have done the similar thing with another material, which is DMS or dimethyl sulfoxide.
Nusrat, sorry to interrupt. You've only got 3 more minutes, so maybe you want to move on to your results soon.
Okay. Thank you so much. Okay, so then yeah, let me quickly finish it. So the main limitation of this work, that even though they have combined these two ideas, they couldn't produce high Q resonance, which actually hindered to get more pure colors. So now let me move on to my structure. So before I actually proposed my structure, I tried to investigate two things, special one thing actually, not two. Just I tried to see which line shape or which spectra is giving me better color. So I investigated it based on two line shapes. One is Lorentzian, another is phaneroprofile. So what I could realize that Lorentzian profile, the colors that I could produce based on Lorentzian profile could give me better color quality than phaneroprofile. Then based on this realization, I tried to propose my structure, which I am going to show in this slide. So this is my structure, which involves two tilted ellipsoids. The material used here is gallium phosphide, which is obviously high index material and is transparent in the visible region. And we're in addition to using gallium phosphide, I have also introduced here an additional layer, which is an anti-reflective coating layer. And the material used here is silicon nitride. The purpose of using this additional layer is to suppress reflection from the substrate so that I can reduce the contribution of higher order modes outside the main reflection peak to make the spectrum more monochromatic, sharp, and to narrow down its bandwidth. So which will eventually help me to produce a relatively pure and pure colors with a large color gamut. So here in the results section, I have only included 3 colors, but apart from it, I have also generated many more. So from these, from panel B and C, what it can be, what is viewable, it is that if I include that anti-reflective coating layer, which I have mentioned, this is the light ash layer. So if I include this, the color quality improves, which can be clearly viewable from panel C, where I have included the anti-reflective coating layer while producing these colors, and the panel B corresponds to colors where I haven't used this layer, additional layer. So to make it more clear, I just included this color gamut where there are two trajectory. The black one, or the black gamut, actually corresponds to the colors which have been produced by in adding that anti-reflective coating layer, and the blue trajectory, it corresponds to the structure where I haven't used that anti-reflective coating layer. So it's quite obvious from these diagrams that if I include that additional layer, obviously I could substantially improve the color quality, as well as I could cover more colors in the visible spectrum. So yeah, this is all about the results that I could produce out of my structure, and this is the methodology. I will not go in detail. I just briefly discuss about the 3 steps. Initially, I have produced these spectra based on some simulation which have been done in numerical. Then I just try to use this spectra to obtain some values of X, Y, Z, which are terms as 3 stimulus values. And based on these 3 stimulus values, my ultimate objective was to get the values of RGB so that I can identify that color and locate it in the CIE color space. So, and in the conclusion section, I just mentioned what I could achieve from my structure. So the first thing is that I could produce high Q resonance, which was never been investigated by any other researchers. Then out of this resonance, I could produce relatively pure and distinct colors. And the color coverage area that I have mentioned here, that I could get out of my design is around 73% for sRGB. I could cover 73% area of sRGB color space, and 69% area of the total CIE color space. So this is all about what I could achieve so far, and still I am carrying out my research to further push this color gamut towards the edge of this chromaticity diagram, so that I can get more coverage, color coverage. Yeah, thank you very much for your attention.
Thank you very much, Nusrat. There is probably time for one question, if we got any questions from the audience. Anne, please go ahead.
Thanks, Nusrat. That's very interesting. I was wondering what substrate you were using, and is it transparent in the visible?
Yeah. It's silicon dioxide I was using. Yeah.
So are you also interested in transmission to create filters and things like that as well?
Later on, probably I will explore further its other application areas. But right now, I am concentrating on designing colors, producing colors.